Hello all, my name is John Gilmore. I'm a current student in the SDM program here, the cohort of 2016. I'm a former Army officer. I was first in the Tactical Maneuver Army, and most recently I was overseeing large construction projects in Saudi Arabia for the United States Army Corps of Engineers. And it is my pleasure to introduce to you Professor Oliver Dweck. He's a professor of astronomics and aeronautics and system engineering. He is a MIT Production and Innovation and Economy Study Executive Director. He's instructor and head of the SDM Corps from 2014 till the present. He's editor-in-chief of the Journal of System Engineering since 2013. Professor Dweck is originally from Switzerland. He holds degrees in industrial engineering from ETH in Zurich and aerospace systems engineering from MIT. Before joining MIT, he was a liaison officer and later an engineering program manager on the FA-18 aircraft program at McDonnell Douglas. Professor Dweck is a leader in system engineering research. He focuses on how complex man-made systems such as aircraft, spacecraft, automobiles, printers, and critical infrastructures are designed and how they evolve over time. Professor Dweck teaching emphasizes excellence, innovation, and bridging theory and practice. He's an associate fellow for the American Institute of Aeronautics and Astronomics and a fellow of the International Council on System Engineering. He won the 2006 Frank E. Perkins Award for Excellence in Graduate Advising. In 2007, he won the American Institute of Aeronautics and Astronomics Outstanding Service Award. And in 2008 and 2011, he won the award for Best Paper in the Journal of System Engineering. In 2010, he won the Capers and Marion McDonald Award for Excellence in Mentoring and Advising. And in 2016, he won the Best Paper Award at the Spring Simulation Conference. Please help me welcome Professor Oliver Dweck.
Well, thank you. It's a real privilege to be here, and thank you, Joan. Thank you to everybody in the SDM program. I'm super passionate about SDM. I started teaching in SDM in 2002. As many of you know, SDM has its 20th anniversary this year, so it's a big deal. It's an opportunity to look back and to look forward at the same time. So what I'd like to talk about in this presentation is really the issue of complexity. Okay, so generally, when we hear the word complexity, we think this is a bad thing, right? We have to reduce complexity as much as we can, but as hopefully you'll see at the end, that's not always the right answer. In fact, in many cases, complexity, if it's invested properly, is a very good thing. And many of the new products, new services that we're producing, and Donna, thank you for your very inspiring presentation, is giving us more functionality, and we have to invest in complexity to get that functionality. So that's really the central theme here. And the other theme is that, like I said, SDM is 20 years old, and a question we constantly get from our colleagues in other parts of the School of Engineering, the School of Science, is what are really the fundamental underpinnings? Is there a science underlying system architecture, system engineering? What's the first law? What's the second law? We know what that is in thermodynamics, for example. It's well established. So are you building products based on heuristics, rules of thumb, or are you building them based on a rigorous scientific foundation? That's really the essence of what I want to talk about. And I'd like to acknowledge here, since mentoring and advising is very important to me, and working with talented students and researchers at MIT has been one of the most really high privileges over the last 20 years. I'd like to acknowledge Dr. Kaushik Sinha, who's here in the audience. A lot of the work that I'll present is based on his thesis work, and then also Narek Shagarian. Where's Narek? Is he here? A doctoral student who's worked with us as well. So 3 questions we're going to pursue. The first one is, why should we care about complexity? What it is, how we quantify it, why is this even an important topic? The second question is, assuming we agree that complexity is important, how do we actually quantify it? If you can't quantify something, it's really difficult to manage it and to know whether you're on the right track. And the third question is, assuming we know how to quantify it, how do we use that knowledge to better manage complexity in our products and in our services? So I want to start with the news. We often do this in the SDM core now. Like we start every lecture with, what's in the news and how does it relate to what we're talking about in class. So this is a very recent story, and we'll come back to this throughout. So in aviation, there's a very new engine. This is the gear turbofan engine that's been developed at Pratt and Whitney, one of our regional great aerospace companies. Been developed over decades. And what's special about this new engine is that it has, and it sort of looks tiny here, it has a gearbox that separates the fan. This is where all the air comes in. About 10% of the air goes through the core and actually provides the combustion and the energy conversion. About 90% of the air goes around the core and provides most of the thrust. But this gearbox decouples the fan from the high-pressure spool and the low-pressure spool. This is a two-spool engine. And allows you to run the fan and the core of the engine at a different speed. So you can run the core faster, and it gives you about 15% better fuel economy, about 70% less noise emissions. But you're buying that improvement with more complexity. And so we'll look at the increase in complexity, not just due to this gearbox here, which looks pretty easy. You just put in a gearbox. But it's the knock-on effects of, the control system gets more complex. You need to provide more cooling. It's all the utility and support systems around it that also increase in complexity. So we're buying better performance, better environmental performance, but at the expense of an increase in complexity. And why is this relevant? Well, first of all, it's been reported that Pratt has invested about $10 billion in the development of this new engine. So that's a very substantial investment. And the engine has about 800 parts. And right now, Airbus is the prime customer for this engine. This is the Airbus A320neo, the new engine option. And the complexity increase is so large that the production targets and the integration of this engine onto the airframe has been much slower than expected, to the point where promises and delivery schedules have had to been slipped, and it potentially has a big business impact. So the increase in complexity has a direct impact on promises, delivery schedules, and eventually market success of the engine. Okay, but let's go back a little bit in history. So one thing I always try to do, I have a fairly long commute, I live out Metro West, is to listen to audiobooks. That's my way to make the commute palpable. And I listen to about 20, 25 books a year, which I greatly enjoy. So I want to tell you about a book, but what have you guys been reading lately? Maybe not related to work. Any great books people have read recently? Yes?
Habits.
Habits, okay. What is that about? I guess habits.
The pattern of habits.
Okay.
Break habits, change habits, both people and organizationally.
Interesting, great. And who's the author of that? Okay.
I will tell you.
Great. Unfinished Business. Any others?
Scarcity.
Okay.
Scarcity, it's about how scarcity affects our cognitive low capacity.
Oh, interesting.
The Generals, it's about history of American military cultivating leadership and swapping people out for these.
For different leaderships, it's a historical book. So I want to tell you about a historical book as well that I read. And this is David McCullough's book. Maybe many of you know David McCullough has written extensively about U.S. history, twice Pulitzer Prize winner. So this is his latest book. It's essentially the history of the Wright brothers. It's a remarkable book. I highly recommend it. And the Wright brothers are really kind of like the entrepreneurs, right, of aviation. 1903, first documented heavier-than-air flight, sustained flight. And it's really interesting because there was a lot of efforts were made to actually not give the credit to the Wright brothers that they were owed. In the US, one of the pioneers of aviation, Samuel Langley, was really the establishment person who was working on heavier-than-air flight. He had large budgets, support of the government, and failed. There's some spectacular video of, essentially all the failures. So the Wright brothers were sort of very much under the radar screen. And what's interesting about it is, how did they achieve this success? It's very much a story of bio-inspired design. So they traveled, as many of you know, they traveled to North Carolina, and they spent weeks and months observing birds. How do birds fly? How do they warp their wings? And really, that inspired sort of the architecture of the Wright Flyer. And so if you look at the Wright Flyer today, it's hanging in at the Smithsonian. And actually, what a lot of people don't know is, like in 1916, 100 years ago, when our campus here in Cambridge was opened, this was the first time that the Wright Flyer was reassembled and displayed to the public in the US in what's today Building 33, where I have my office. So let's take a look at some of the details behind the Wright Flyer. And it was a very elegant architecture. So we have essentially, the Wright brothers were bicycle builders, so they used a lot of their skills and materials from building bicycles. So we have the elevator here. This is for pitch control. And what's pretty unusual today is this hip cradle. So the hip cradle, basically, the pilot would slide his hip back and forth, and by doing that, this hip cradle was connected to cables to the wingtips, and this is what would warp the wings to provide roll control. Much later then, that was replaced with ailerons, right? Rigid flight control surfaces. They did have instruments, actually. They had a couple instruments. There was a stopwatch. The engine development is treated extensively in the book. This was a big, big advance to provide an engine that had sufficient power to weight ratio to achieve flight. And the rudder, of course. And then there was a water reservoir, gas tank, really just the bare bones essentials. So then let's fast forward. Many of you have heard of Augustine's Laws. Norm Augustine, former chairman of Lockheed Martin. He wrote a book starting in the 80s called Augustine's Laws. It's been quite successful. This is 1997, the 6th edition. And there's a bunch of laws which mainly are extrapolations. And some of these extrapolations that he's making seem really far-fetched. But the reality is many of them we're still tracking on. So this is Augustine's 16th law. So here's the Wright brothers. We just talked about them, 1903. And this is essentially the cost of a single airplane, right? And then here's time with some projection. And so if we look at the cost of, these are mainly military aircraft, but how the cost of an individual aircraft has increased, and then we extrapolate the defense budget, the gross national product, this would tell us by 2060, the entire defense budget could only buy one airplane. And then the services have to share, right? The Navy gets it on Monday and Wednesday, and the Air Force on Tuesdays and Thursdays. And then, by the 22nd century, it'll match our gross national product. So, we're still in every edition of the book, he sort of updates it, and we're still on that trend. So the question, of course, is what's going on, right? Why this escalation in cost? And DARPA, our Defense Research Projects Agency, actually did a study on this. And they found that the slope of that curve that I showed you is roughly 10% per year. That's the annual escalation rate of cost of these systems. And where does it come from? Well, a part of it is due to the underlying economic factors, labor, equipment, material. So you could say that's more or less inflation related. So let's take that out. But what you see, what's left here, some of it is regulatory, production rate, and learning, meaning the fewer airplanes you make, the less opportunity you have to learn and get more efficient, and you have a sort of vicious spiral. But by far, the largest factor is due to the increase in complexity. More functions, more software, more resilience, and this increase in complexity is the biggest driver of the increase in cost of these systems. And where's that coming from? Well, it's coming from requirements, right? Functional requirements. We're asking these systems to do more and more, to be more resilient, to survive in more different environments. And this is a very well-known, this is a classic chart that was put together by the AIAA MDO committee several years ago. And what it shows is, again, over time, the layering of functional requirements that happen in aviation. So again, here's the Wright brothers, right? 1903, 1G flight. Take off, fly for 30 seconds in a straight line, and land. That's it. That's the requirement, right? Check. What was the next thing? Maneuver and gust accelerations. Really interesting. Again, going back to the McCullough book, nobody in the United States really knew or believed that first flight had been achieved. It was virtually unknown. It was not in the news. It was not a big deal. So the Wright brothers actually went to France, 1908, 5 years later, crated up their airplane, assembled it again, essentially rebuilt it almost from scratch in France, and then did for weeks and months at a time demonstrations at a racetrack outside of Paris, flying in a circle for hours at a time with thousands of people watching. And finally, news came back to the US that, oh, maybe we should have paid attention to these guys, and the story sort of got out. But what's interesting is those flight demonstrations that were attended by thousands of people, sometimes 10,000 people would show up and you couldn't fly because the wind was a little too strong, right? So the conditions had to be just perfect to do these flight demonstrations. So one of the very first new requirements was, well, maybe we should be able to turn. That would be good. And we should be able to fly over a bigger range of wind conditions. So that's your next layer, maneuver and gust acceleration. And then, as aviation really took off, and it went very quickly after that, in the 1909, 1910, 1912, World War I had a big impact as well on aviation. Airplanes got faster, they started flying higher, longer, and at some point, about 10 to 15,000 feet, you start to get to a point where you need to start pressurizing the cabin. And you start moving from wood and fabric to metals. And then you need to think about corrosion control and pressurization. And then you see a big step here in around World War II. That was another time when aviation took a big step forward. And you get a whole nother range of requirements, laminar flow, handling, radar, big work at MIT as well in World War II, right? We had a big impact in radar development. And another big step. And then more recently, we care about fly-by-wire, producibility, affordability, supportability. What does it actually take to keep an airplane flying? How many man maintenance hours per flight hour does it require? So that's the reason, this increase in requirements is the reason behind the increase in complexity. So the way we can think of it, we're going to come back to this chart a couple times, is we start with customers and competition. Without customers and without competition, if you're a monopolist, you just provide a one-size-fits-all solution and collect your rent, and that's it, right? The reason we care about complexity, the reason that functional requirements keep going up is because of competition. Whether it's commercial competition, whether it's military competition, competition is the fundamental driver behind all of this. So the competition drives requirements, and the requirements drive what we call functional complexity. What is it actually that the system has to do? The functions, the range of requirements or environments that it has to survive in, that's the big driver. And given the functional complexity then, how do we implement this? What are the technologies, the architectures that actually make up the system? So the functional complexity drives the structural complexity, which is what we typically see and what's, in a sense, easy to measure. And then as structural complexity goes up, sometimes we get emergent behaviors. The system does things we didn't ask it to do, but it's doing these behaviors, sometimes surprisingly, as a byproduct. And so then we need to think about how to mitigate these emergent behaviors, and we get into this loop. Okay? So that's essentially our starting point for structural complexity quantification. So I went back and said, all right, so how complex was the Wright flyer actually? Can we quantify the complexity of the Wright flyer? And this is essentially a DSM, a design structure matrix. Many of you have seen this before. It's essentially a matrix that captures at some level of decomposition all the elements of the system. So this gets back to the picture I showed you of the Wright flyer, the fuselage, the wing, the wheel hub, the instruments, the pilot himself, the elevator control, the hip cradle we talked about. And then these off-diagonal cells show you the different interfaces or connections. And fundamentally, in any cyber-physical system, there are only 4 kinds of connections. Physical connections, so part A is physically connected to part B, which means that you can transfer forces and torques across that interface. Mass flows, so that's fuel, water, exhaust, energy flow, and then information flow. And we have all these types of flows in the Wright flyer. So for example, if we look at the hip cradle, where's that? You can see here the hip cradle, the pilot is connected to the hip cradle. And you can see that the hip cradle is then physically connected to the wing and, of course, the cables, right? And then the cables are connected to the outer wing, and that's how it works. So that's essentially the architecture of the Wright flyer. So in total, we have 62 physical connections, 4 mass flows. That's mainly the fuel and the air and the water for cooling. 11 energy flows, 9 information flows. So there were some instruments, very primitive, so an pressure instrument to measure the airspeed and a timer, essentially. 9 information flows for 86 total connections. And if we look at the density, how many connections are there in the system? Over the total number of components, we get a density of about 7%. The other thing interesting we'll come back to is each component in this architecture has about 5 interfaces on average. 5 interfaces, and that's our K here, that's the nodal degree. And we'll come back to that number 5 or 6 later. All right, so that's hopefully motivation for why we care about complexity. So now, how do we quantify complexity? And there's a huge literature on this. There's a journal called Complexity. There's a lot of work. And one of the people has really written about this very deeply and has been recognized for this is a lady called Elaine Weicker. She is a software engineer, and she was really interested in quantifying the complexity of software. And she said, no matter what metric of complexity you're proposing, it should meet these criteria, Weickers Criteria. A valid metric of complexity should demonstrate the following broad characteristics. I'm not going to go through all of them, but just highlight a couple. So, for example, it should be invariant to relabeling. Just by relabeling or reordering, for example, the DSM, it shouldn't impact the complexity. You should be able to have different architectures at the same complexity level. The system structure, the structural complexity we talked about, should at least partially determine the complexity of functionally equivalent systems. Changing the subsystem interface patterns should have an impact on structural complexity. So essentially, Weickers criteria are a test that you can apply to any proposed complexity metric. So after a lot of work, and again, this is sort of Kaushik's thesis here, after many years, and looking at many different complexity measures, this is the one that we converged on. And it's a structural complexity measure. So it measures structural complexity. And it looks kind of scary here, but essentially, if you could just focus on this equation here. Structural complexity of the system is equal to C1 plus C2 times C3. So what is C1? C1 is the complexity that's in the individual components. Okay, so if we took the Wright flyer apart, which has been done, you spread all the parts out on a big parking lot, each of those parts individually has complexity. That's the first term. And since the complexity of the parts could be different, this alpha, the alphas are individual component complexities. The second term is more interesting because this has two parts to it. One is the complexity that lies in the interfaces, the bilateral interfaces between neighboring components. Those are the betas, okay? And then this term here, which is often forgotten. So most measures of complexity either count components, they count interfaces, and then add them up in some fashion. But they forget to account for this third term. This is the C3 term. And this is basically what we call graph energy. It's the energy that's in that DSM matrix that you saw. It's a mathematical form of energy that captures the topological complexity of the system. So the arrangement pattern of the parts itself has complexity. Not just the parts themselves and their interfaces, but also the topology of the system. And you can see it's multiplicative here. How do we calculate graph energy? It's actually a very elegant, easy calculation. Given a matrix A, this is our DSM or adjacency matrix, we do a singular value composition, which is like the eigenvalues of that matrix, and we add up all the singular values. That's the total matrix energy of that system. And we'll look at some examples. So where did this come from? Where did we find this? How did we adapt this? It turns out that in quantum chemistry, this has already been done. So chemists, and in chemistry, the question is, how can we quantify rigorously, based on physics and chemistry, the complexity of molecules, in particular hydrocarbon molecules? So here's a molecule. It has two benzene rings. You can represent it as a graph. This is the matrix of bonds, right, that the molecule is made up of. And it turns out that it's the Hamiltonian. The Hamiltonian, so this is not Hamilton on Broadway, right? We all know Hamilton on Broadway. That's a different Hamilton. This is Sir Rowan Hamilton, who lived in the 19th century and reformulated Newtonian mechanics. And essentially, what we find is that the molecular energy is essentially a C1 plus C2, C3 equation. So the first term is the energy of each atom on its own, right, in this molecule. And a hydrogen atom will have a different energy from a carbon atom. And then the second term essentially is the energy that's in the bonds and in the molecular arrangement. And so what we're saying here is, if this is applicable to quantum chemistry, this is also applicable to more macroscopic systems that we're designing, that we're interested in, for example, in SDM. So you can apply this to cyberphysical systems. So here's a very simple example. This is from Denman James's thesis, who's at Pratt and Whitney. So there's a valve, a pump, a motor, controller. Again, you have physical energy, mass connections. And here's your adjacency matrix. And one of the challenges, though, when we do this for macroscopic systems is, since we're not at the atomic level, is what are the alphas and betas? So what are the proper values to select for component complexities and interface complexities? And so in some cases, there may be some uncertainty as to what the right component complexities are. And rather than getting a single number, you might get a distribution for structural complexity. We can talk about this later, but you can apply this to cyberphysical systems. We also did some experiments, human experiments, and said, so does it matter, what's the impact of increasing levels of complexity? So we said, what experiment can we do to quantify this? So what we did is basically got these chemistry kits that you probably all remember from high school. You can build all these different molecules with different bond types. And so you have a ball and stick chemistry toolkit. You provide images of different molecules of increasing levels of complexity to a set of test subjects. And you ask basically them to assemble them correctly. And then you measure how long does it take. And that's what we did. So here's the structural complexity. And the hypothesis is that as you increase the complexity of the system, two things happen. One is you slow down, right? You slower progress, and this is due to hitting the limits of our cognitive abilities. And the second is a higher error rate. You will start to make errors as the complexity goes up, and then you have to rework to fix those errors, which are included in the total time. So we basically designed the experiment. We picked 12 different molecules of increasing complexity. So N is the number of atoms from 3 to 46. M is the number of bonds. Here's your C1, C2, C3, the three components of complexity. And then here's the total structural complexity, which goes from about 0.68 to about 16. So roughly 1.5 orders of magnitude increase in complexity. We conducted the experiment with, in this case, 17 test subjects. And this is the mean build time in seconds versus the structural complexity of these molecules. And so each point here shows the average build time as molecular complexity increases. And what we're interested, of course, is to see what's the shape of that curve. And what we found is essentially, so this is the functional form of this solid line. Y equals ax to the b. Y is the total build time. X is the complexity. And we were really interested to know what is b, this exponent. And what we found in these is that essentially the exponent is very close to 1.5, about 1.48. So what that means is if you increase the complexity of the system by, say, 50%, the actual cost of building that system is going to increase more than 50% because of the superlinearity. But it's less than quadratic. And when you look at stories about this project is over budget or is under-delivering to the promises, we think one of the major reasons is because this effect here is ignored. You increase the complexity, but the effort to deal with that complexity increases superlinearly. And people don't know that and forget that. So that's important. The other really interesting thing we found, and this is more of a qualitative observation, is that there were some big differences among the individuals in the experiments. Some people are much better than others at handling larger levels of complexity. And you can see this by looking at, this is build time, or complicatedness is the perception of complexity versus the actual complexity. So you can see that some people, they're on this curve, and as complexity increases, they hit the wall, right? They just can't deal with this. And other individuals change what they're doing as they're hitting a certain complexity level. And then they're on a different curve, and then they change again. So you can see it in the experiments by looking at what people actually do. Some people assemble a large molecule, a really complex molecule, the same, a small one and a little one. Other people step back and say, at the large molecules, wait a minute, there's structure here. There are modules here. Do you remember those benzene rings? So what they say, I'm going to split this and I'm going to do pre-assembly of the modules. They see the modules. They see the system at a higher level of abstraction naturally. And other people can't do that, or they don't see it naturally. It's really interesting. So getting back to Weickers criteria, here's a list of complexity measures that have been proposed in the literature. Number of components, number of interactions. Dan Whitney, who spent many years with us, did a great job in this area as well. Number of loops, nesting depth, Cobra complexity, et cetera, et cetera. And then is it actually computable, and does it satisfy Weickers criteria? So we claim that this particular measure of complexity that includes matrix energy is relatively easy to compute and satisfies all of Weickers criteria. So that's why we're using it, and we think it's rigorous. Okay, last part of the talk is really how do we manage complexity better, knowing what we know now. So first of all, when you look at an architecture of the system, maybe the fundamental question is it a centralized architecture or is it decentralized? This is a big question. It's in the internet, in transportation. Should we have a few elements that are the hubs, the dominant elements, or should we have a more spread out architecture? That's one of the very first order questions when you look at architectures. And it turns out that our C3 term gives us the answer to that question. So a centralized architecture, in the extreme case, has one hub, right? This guy right here. And then every element is tied into that hub. Many systems are hierarchical, so there's modules or sub-hubs. And a fully distributed architecture has no hubs. And it turns out, when we look at the C3 term, that the transition between these regimes is very clear. Okay, so centralized architectures are, we call them hypoenergetic. Their C3 term, their graph energy, normalized graph energy is less than 1. And then in this transitional regime, your C3 term is between 1 and 2. And for distributed architectures that are hyperenergetic, C3 is greater than 2. And that's really helpful to understand, where does your architecture fit in on that spectrum between highly centralized and highly decentralized. So we then applied this to a number of real-world industrial case studies with the main goal of showing, by how much does the complexity of a system increase as we progress in technology, as we infuse new technologies, and what's responsible for that increase in complexity. So here's an example from work we did with Xerox. So here's a Xerox printing multifunction office machine. This is the graph with all the components and all the connections. We compute a complexity of 186 here. And then here's a new generation. This is the iGen 3, iGen 4 digital printing system. And it has a complexity of 354. Okay, so this is a 90% increase in complexity, essentially from one generation to the next. And we can look at it probabilistically. The interesting thing is, if we look at, again, the C3 term, you see the C3, here's our C3 term for the new system, the new machine over here on the right, and then the older machine on the left. It has a C3 of 1.36, the new machine of 1.8. So we're still in this middle regime, right, of hierarchical architectures, but we're moving much more toward a distributed system. Second example, coming back to the aircraft engines. On the left, we have an engine. This is a classic direct drive two-spool engine. This happens to be the Pratt & Whitney 4096. That's the engine used on the Boeing 777, which is still a very successful airplane. And then here's our new gear turbofan engine. Complexity calculation, the structural complexity increased by 42%. All right? Now, we have a similar phenomenon in terms of C3. But the architecture is not that different, 1.51 versus 1.69. We do have substantial increase in number of components, but again, it's not that much. The gearbox, a variable area nozzle. The real increase here is in C2. And that's what I was saying earlier. It's you put in a gearbox, you put in a new technology, but now it's all the other things you need to do to integrate that technology. The controls, the cooling system. That was the big driver on complexity increases here. And all of that has to be tested and certified under all flight conditions. And the big challenge has been, in particular, the startup of the engine. Once the engine's running at steady state, it's not as big a challenge, but it's getting the engine started up quickly and reliably. That's been the big challenge. So 40% increase in complexity. And as we saw from our experiments, that doesn't mean 42% increase in the R&D budget, right? The actual increase in R&D effort is more than 42% because of that nonlinearity, because of the human cognitive limits. And that's what's often forgotten. So let's talk a little bit about underlying fundamentals. And I told you, at MIT, we always get challenged every day. And one of the challenges is always, what are the fundamentals? What are the fundamental insights, laws, theorems, things that really are at the basis of what you're doing? We found a couple of quite interesting things. One is the idea of a P point. So P stands for phase transition. And that's essentially the idea that in any system or product, there's a tipping point in complexity. You can increase complexity and you get benefits for it, but there will come a point where if you go beyond this point, the P point, it's not worth it anymore. You continue to increase the complexity and cost, but you're not getting the benefit for it. And that point happens to be the knee in this curve. So this is the diameter of a network. Could be a transportation system. It could be an information transmission network. So initially, your system is very sparse, right? You just, for example, have a pure hub and spoke. So everything has to go through the hubs. And you're like, well, that's a long way around. Let's start to add some links. Let's make it denser. So you move to the right. So you start adding links, and the performance gets better and better. In this case, the diameter starts dropping very fast. And then you hit this knee here, where you can keep adding links, but at least the average performance of the system doesn't really improve much anymore. And then here's this for a different, so we can see this in different applications. We can apply this to real product design and look at where is this P point actually. So here's graph energy. This is essentially our C3 term, our topological complexity versus network density. Most real products have network densities in the single digits, 4%, 5%, 7%. And so we're on the left side here. On the right side would be a system that is fully connected, which we don't see that in reality. But mathematically, you can imagine a system where every component talks to every other component. You'd be on the right side. And then this red curve is like a background baseline of mean graph energy for randomly generated systems. This is sort of a background that we compare against. You can see that the most complex systems would be those that have roughly half their connections and half the other connections don't exist. So roughly in the middle here, most real products are here. So where's the P point? The P point happens to be if you take the graph energy of a fully connected hypothetical system and you follow this line and you intersect that at the low density end. So the P point is the low density equivalent of a fully connected system in terms of graph energy. And what we found, lo and behold, is most real products are right at or right below the P point. So here's the printer, here's a V8 engine. And what this says is, look at your systems, look at your products, quantify their complexity, and look whether you're at the P point or above. And if you're above the P point, you're essentially you're at a point where increasing complexity more will probably not yield value. There's another remarkable thing that happens at the P point, and this gets to the average number of interfaces or connections per node. So here's again our P point. So when we look at the size of the system, in this case the design structure matrix, versus the number of critical connections, where the matrix essentially becomes full rank, we can see that even though the critical density is dropping as the system gets bigger, the critical average degree is constant. That's remarkable. That's a remarkable property. So about 6 connections per part is the critical number of interfaces per part at which the system becomes full rank and where the P point is reached. And there's a lot of other research that says that this nodal density of about 6, or this average degree of 6 is critical. This is work by Valenti on network resilience. So this is where you have a network, and then you have either random or targeted attacks on that network by taking out nodes or edges in the network. And the question is, will it still work? And so this is the residual, essentially the performance of the system as a function of number of nodes or edges knocked out. And you can see, again, the contour here with 6. This is some of Dan Whitney's earlier work where he looked at DSMs, the number of marks in the DSM versus the size of the DSM for things like the Intel product development process, throttle body, a door subsystem. And he basically did a regression and found that the regression is y equals roughly 6.3x minus 67. The interesting thing is the 6, right? Very, very fundamental. What was the number of average connections in the Wright flyer? 5, right? Below that, just below that limit. So we think that's critical. So talking about managing, how does this help us manage complexity better? Well, let's think about this again. So we have structural complexity over here. This is the actual physical complexity of our products or services, whether it's a software platform, a physical system. That's measurable objectively. That's not in the eye of the beholder. And then we're filtering this through a human cognitive process, whether it's an individual process or a team-based process. And that's our perception of complexity, which then leads to the actual effort, the system development cost. And we've seen earlier in the experiments that the relationship is nonlinear. So here's your development cost, here's your structural complexity, and the experiment suggests the exponent here, which is really the key, is somewhere around 1.5. And how is that driven? That's driven by the complexity itself. How have you been able to modularize or encapsulate the design? How novel is it? And then there's cognitive abilities and bandwidth and also cultural effects. So in this case, what it means, if you believe this 1.5 exponent, is that a 42% increase in complexity will translate to a 69% increase in R&D costs. Getting back to the Pratt and Whitney example, you heard the figure of $10 billion invested in that new engine, which is a stunning number. But now we can understand better how that can happen. So our early diagram of the dimensions of complexity is not complete, since at that level of complexity, no individual can understand the whole system. We need teams, we need organizations. So the structural complexity leads to organizational complexity because we need to distribute the development effort. And then, of course, we can have feedback here with team structure and interactions. This, by the way, is known as Conway's law, homomorphism, that the architecture often will mirror the technical architecture often mirrors the organizational architecture. And that drives the non-recurring engineering costs, the schedule, and then, of course, you can have backdriving from the organizational complexity to the functional complexity. So that's really the full picture. Functional complexity driven by competition drives structural complexity, drives organizational complexity, and then you have feedbacks there. So getting back to this question of heuristics and system engineering. So what's one of the most famous heuristics that you've heard in designing a system? One of the most famous rules of thumb. Form follows function. Yes, definitely agree. 80-20. Yep. Yes. KISS, right? Keep it simple, stupid. KISS. And it turns out KISS is a good heuristic for some systems, but not for all. So if we think about those two key relationships, so one is the complexity driving non-recurring engineering. Here we have our nonlinear equation with this exponent m. We think it's about 1.5, but it probably differs by domain and by these other factors like training, cognitive bandwidth, culture, and so forth. And then here's an assumed curve for performance of the system versus complexity. So in many technologies or systems, you will have a little bit of increase in complexity early on gets you a lot of performance gains. And then as you want more performance, every % increase in performance is you have to fight for it very hard. A lot of complexity increase. That's really where we're at in the aircraft engines. Aircraft engines are very mature, they're very reliable. Every % improvement in fuel efficiency, noise, reliability, you have to fight for it very hard. So in aircraft engines, we're like in this part of the curve here. So what's interesting is when you parameterize these relationships, here's the equation for performance versus complexity. And you can see there's an exponent here. This is a classic S curve, a logistics curve. We have this exponent n. And then in the complexity versus effort curve, we have an exponent m. And it turns out if n is smaller than m, in other words, we're sort of in the flat part, it turns out that the value maximizing design, we define value as performance divided by effort, is in fact In this case, where n is smaller than m, you should go for the simplest architecture that satisfies your minimum performance requirement. So you have some minimum performance requirement that you have to satisfy. Go for the simplest architecture. That's exactly what the heuristic says. However, for systems where n is greater than m, right? And those are systems essentially where there's a lot of gain to be had still for little improvement, little steps in complexity. It turns out for n greater m, there's an optimal level of complexity. That's this point here on this value versus complexity curve. You want to find that point. This is the sweet spot. You're building in more complexity than you really need to based on a minimum performance requirement, but you're doing it to maximize value of the system. Okay? So that's, we think, is interesting because this now leads us to the notion of complexity budgeting. We budget for everything. We budget for mass, power, financial budgets, but very, very few organizations deliberately have complexity budgets. And we think that's where the field needs to go. That's where system engineering needs to go, is setting targets for complexity. And as we talked about, complexity has these three subcomponents. C1, component complexity. C2, interface complexity. And C3, topological complexity. So this curve that you see here, this is notional, but this is an isocomplexity surface for a system that has 20 components and a total complexity of 100. And so a complexity budget would say, you can design any system that satisfies the requirements as long as it's on this surface. And then you can decide, is it better to make a system that has fewer components, but each component is more complex, right, and has fewer interfaces? Or are we going to go for a system that has a lot of components, but each component is simple, but the intricacy is in the architecture, in the arrangement? The total complexity would be the same. And that's where we see the distinction between companies that are excellent component designers, they're really good at component technologies, and companies that are really good system integrators. Okay, so that's really where we think things should go. So then finally, what's the first law? The first law, when you look at first laws in engineering science, this is what you'll find most likely. The first law of thermodynamics, about 1850. And the first law, it's most first laws in any field are conservation laws. Conservation of mass, in this case, conservation of energy, and it says that the total energy of an isolated system, so you have a system boundary, a control volume, is constant. You can only transform energy from one form to another. You can't create or destroy energy in a closed system. And these are the three terms: the kinetic energy, the potential energy, and the internal energy of the system, this term U. And it's pretty interesting. We take this for granted, but it took almost a century for the first law of thermodynamics to be universally accepted. There was a lot of back and forth, a lot of reformulation, and now it's solidified and generally accepted. In system engineering, we're basically where the thermodynamicists were in the 19th century. Okay? So here's what I would say is the first law of system engineering mirroring the first law in thermodynamics. And the conserved quantity here is complexity, conservation of complexity. So given a set of functional requirements and associated performance level, the total complexity of a system is conserved, and complexity can be traded between the components, the interfaces, and the topology, but you cannot decrease the complexity beyond a certain limit, given what you're asking the system to do. And so, the total complexity then is C1 plus C2 times C3, plus this term W, which is the equivalent of the internal energy, and that's the one we're really still trying to figure out. What does that really mean? That third term, that's one that we're still researching. Why does it matter? Finish with this example, the space shuttle. You all know about it. It was retired in 2011. There's a really interesting paper by Pilkey that came out in Nature on the history of the shuttle program. So number of flights, total money spent, about $192 billion we spend on the shuttle, and we got 135 launches out of it. Great system, but very complex, very fragile in a sense. And, this is the vision, right, what we wanted. This is a figure from the 70s when the program was essentially started. And then this is what we actually got. Right? This is it's in there. The orbiter's in there. This is a picture from the orbiter processing facility, and the effort that it took to get the shuttle turned around for each flight was very large. So I think with better complexity management and explicit complexity budgeting, going into the future, hopefully we can avoid surprises like this. So with that, we talked about why you should care about complexity, how to quantify it, and how to better manage it, and it's an ongoing journey and an ongoing challenge. So let me just summarize. Structural complexity has been increasing steadily since the Industrial Revolution, and that'll continue. It's really driven by competition, customer needs. These three types, functional, structural, and organizational complexity. The human cognitive bandwidth limitation, this magic number 7 plus or minus 2, we talk a lot about it in the SDM core. The idea that the complicatedness, our perception of complexity, really drives superlinear costs and effort with that exponent 1.5. Rigorous measures of complexity, there's a number of them, but we're very excited about the one that's based on graph energy. We think it satisfies Weickers criteria and has these three major elements: component complexity, interface complexity, and then topological complexity. And where we need to go collectively is better complexity management. And the good news is there's some real anchors for us to do that. The P-point, critical transition, the critical nodal degree of 6, and then the idea of isocomplexity-based budgeting. So with that, I hope it was not too heavy on the math, but we have some time for questions, right?